Okay, so 4.1, antiderivatives and indefinite integration. Okay. We are going to be working on antiderivative. Well, what do you think antiderivative means?
The inverse of a derivative.
Okay, it's the inverse operation of a derivative. We need to undo those. We are just going to be introduced today and tomorrow of what those are. We're going to bear very basic integration, and then what it is used for is in 4.2. And then when we come back from break, we'll start getting into all the product and the substitution and all those rules in there. Okay, but these are going to be very basic antiderivatives to start out with. Okay, so a function f is an antiderivative of f for the interval I if f prime of x equals f of x for all x in I. Okay, so basically it's the antiderivative if we can do the derivative and it works. Okay, so it says find the function f whose derivative is 3x squared. So we have to go backwards. So f was what?
Well, we know that the exponent, or the power, is going to be 3.
Okay, we know the power was 3.
Yes.
Okay.
X cubed.
So it was x cubed? Yes?
Yes.
Okay. So we just took that backwards. Now they're not going to all be that easy, but
Wait, can you re-explain that?
so if I started with x cubed, what would the derivative be?
Oh, I see.
It would be the derivative would be 3x squared. So we are not going to get into the product and quotient and all those. Okay, we're just doing basic ones
Thanks.
for now. For now.
Will that be like a next semester thing?
Yes.
Awesome.
Okay, so what we have here is we had f equaled x cubed, correct? But couldn't it have been x cubed minus 5?
Yeah.
Could it have been x cubed plus 97?
Yes. Because those are zeros.
Those are zeros, right? So what we had actually was an antiderivative, not the. Does that make sense?
Mm-hmm.
Okay, so x cubed was an option, but it could have been x cubed minus 5, and it could have been x cubed plus 97. It could have been x cubed minus 16 over 5, right? Those are constants. So what we do is we write it as f of x equals x cubed plus c.
If they asked for the...
No, it just if they would say find the antiderivative, or it may say find an antiderivative. I'm not sure, but anyway, what we do, what does that c represent? A constant. Any constant we can throw in there. So I'm just going to put some definitions up here, and I don't know why I changed it to whatever I did. Okay, so all the antiderivatives of f of x equals 2x is f of x equals x squared plus c. That's all of them, yes? Because I put a what?
Constant.
I put a plus c. This is called the family of all antiderivatives. And c is called the constant of integration. And x squared plus c is called the general antiderivative of f. We will be finding tomorrow the antiderivative. So that means we're going to have to solve for what? C. So it's important that you do the assignment today so you're good at finding the antiderivative. So tomorrow we can solve for C.
I'm so confused. I couldn't C be anything?
Well, it can be anything until I give you another condition.
Okay.
Once I give you another condition, then we're going to find out what C is. But so today we need to be good at finding general solutions, so tomorrow we can find the solution. Okay, again, why is it called the general antiderivative? Because of the what? Because of that plus C. We will lots of times just be finding general until they say the point whatever, and then we can find out the exact. You good? Okay, so find the general solution of the differential equation. It's called differential equation because it's prime, yes? Of the derivative of y equals 2. So what was there? 2x. So it's y equals 2x, but then we have to put a what? Plus c. Now I think what's going to happen is a picture is going to come up. Yes. So let me rewrite it. So I have y equals 2x plus c. Yes? So this is a linear equation. Yes? With a y-intercept of c and a slope of 2. So if I change the c, is it going to change the graph that I would get?
No.
It wouldn't?
Yes.
Yes? Because c is your y-intercept.
Yeah.
Yes? But these lines are all parallel because they have the same slope. But it changes where it hits the y-axis. So do you see how that can affect it? Now, it's very general. It's a linear equation. Right now, we're not dealing. You will deal with square roots and cubic and quadratic today, but just I wanted to show you that's what happens. Okay, so just give this a minute. Don't just start writing. Let's read through it. It says, when solving the equation in form dy dx equals f of x. Well, what does dy dx mean? Derivative. Okay, so the derivative of y with respect to x of x equals f of x. So f of x would be the antiderivative, correct? Okay, so it is convenient to write the equivalent definition in the form of dy equals f of x dx. How did I do that?
You added
Multiplied over the denominator, didn't I? That's it. Okay, so dy, then we would just have y equals so what I have is the operation of finding all the equations is called anti-differentiation or indefinite integration. Either one can be used, or sometimes they just say integrate. And this right here is the integral sign. It's like a tall, stretched out S. So what we do is we rewrite this as y equals the integral. That's what this is, the integral of f of x dx now they have things. The f is the integrand, so they call it the integrand, and the dx is just telling you what variable you are integrating. Isn't that always been what its job is? It was the variable, it told you the variable that you're differentiating, didn't it? So that's its job. So if we wanted y, it'd be dx, and then it would be dy on the other side. So we can simplify that after we find the solution of the capital F they use as the antiderivative of f, and c is the constant of integration. So this integral, when I see this integral sign right here, it tells me to integrate, yes? Once I've done it, does the integral sign continue with the answer? Is there an integral sign here? No. It's just like a square root. When you take the square root of 4, the answer is plus or minus 2. It isn't the square root of plus or minus 2, is it? We read it as the antiderivative of f with respect to x. That's how we read this statement right here. And we will just tend to say the integral of f of x dx. When you hear antiderivative, you should be thinking integral. When you hear integral, you should know you have to do what? Antiderivative. Those two things will go back and forth in your brain. And we've already said that integration is the inverse of differentiation, and differentiation is the inverse of integration. Just like multiplication is the inverse of division, division is the inverse of multiplication. Yes? Addition is the inverse of what? Subtraction. Subtraction is the inverse of addition. Gentry, why are you on your computer?
I have to send this weird invite I had created because it didn't come through.
Probably not the appropriate time. Okay, is everyone good?
I'm reading.
And this is what I just said. They're inverse operations. Okay, this is on in your book. I'm not waiting for, do not even start writing this down. If you want to write it down, it is on page 250.
Do we need it?
This is all the integration rules. You will eventually, you need to know them. Okay?
You expect us to know each one of them.
You should already know all these.
How many should we know for the assignment?
None. Right now. This is just, it's just a we will get there. Okay? So you should already know all the differentiation rules. We are going to start adding the integration rules. Okay, it is on page 250. No, just look at page 250 in the section. It's really easy to find because it's in chapter 4 and we're right on there, right? Okay, their basic integration. So if I have the derivative of the constant, it is what?
0.
0. If I have the integral of 0, it is a what? Constant. Okay, this was kx, yes? The derivative was k?
Mm-hmm.
So we just did this one. The integral of k was kx plus c. If I have the derivative of one term plus another, I have the derivative of each term, yes?
Yes.
So if I'm going to take the integral of one thing plus another thing, can't I take the integral of each of them independently?
Yes.
Yes. Okay, that's about where we're going to go. Now this one, if we look at it, this one that I didn't really mention, we have k of f of x, k is a constant, yes? Is k times the derivative of f. We know that one, right? So, I can take, if I have the integral of k f of x dx, I can bring the k out in front of the integral, find the antiderivative, and throw it back on. So, right about here is where we're going to end for today. I'm pretty sure. Actually, no, I lied to you. We're going to use all of those in conjunction with the next one. So from here up is the general just rearranging of it. Right here is the basic rule we're using. Okay, now the power rule for derivative means you take the exponent, bring it out in front, and subtract 1. Yes? Okay, so we're going to go backwards. We're not going to subtract 1. We're going to what? Add. So the integral of x squared, of x to the n dx is x to the n plus 1 divided by n plus 1. This is the rule that you are going to use for today. Right there. That one. You want to write that one down? You can write down. Do not write all of them, is what I was trying to say before. This is what we're going to be doing today. The basic power rule, just like when we did differentiation, we started off with that basic power rule, didn't we? Okay, so we subtracted 1 for differentiation. We're going to do what for integration?
Why is it over n plus 1 now?
Because when we went one direction, we did the same thing. You'll see why. Okay. Because you have to worry about the coefficient in front. And you have to go backwards from it. Okay, so it says describe the antiderivative of 3x. So we have the integral of 3x dx is equal to, well, this 3 is a constant, yes? So we could put it 3, the integral of x dx. So the rule, what is the exponent on the x right now? 1. Okay, so the rule was x to the n plus 1 over n plus 1.
That's what we just...
That was the power rule that was on the sheet. Okay, that's the power integration rule. So we have 3 in the front times, well, what is n right now? 1. So x to the n, not n, what is 1? N? We said 1, right? 1 plus 1 over n plus 1. So your denominator is what? 2. So that's 3 halves x to what power? Second. Plus c. Okay. So this is, we have y equals 3 halves x squared plus c. Yes? So let's check our work. Check our work. So I'm going to find the derivative now.
How do you know to use that equation? I'm so confused.
Because this is the rule we're using.
Is it going to say?
Today, yes. No, today you are using this rule. Okay, so now I'm going to find the derivative to check my work. So how would I find the derivative? 3 over 2 x squared. So 3 over 2 times what? 2 x to the first.
Yeah.
And the derivative of a constant would be 0. Okay, 2/3 of 2 is what?
6 over 2.
Would be 3x. Is that what we were supposed to have?
Couldn't it have been 1.5 x squared? And you would have got the same answer. 3x if you found the derivative.
Yeah, but it was much easier to deal with when you're multiplying by 2 to do, but whatever. So when you do your work today, it's going to ask you to check it sometimes. Well, checking it is finding the derivative. Just make sure you get what you started with. So a big part of finding the antiderivative is to make sure you rewrite it in something you can do the integral of. We wrote 3x to 3 the integral of x dx, didn't we? Okay, we didn't leave the 3 in there. I've seen people that do leave the 3 in, and they just have bigger numbers, and it's harder to deal with. Shelby, let me know when you're good.
Yeah, sorry.
You're fine. I just saw you were writing still. Okay, so we need to rewrite these. So I have the integral of 1 over x cubed dx. Well, what have we done in the past when we have 1 over x cubed? We rewrite it as what?
1x negative 3.
Cube root.
No, not cube root. We rewrite it as the integral of x to the negative third. 1/3 would be the cube root, and this isn't the cube root. It's cubed. Dx. Okay? So now I'm going to use my rule of x to the n plus 1 over n plus 1. That's the rule we're using today.
So what is the anti-differentiation thing? Why do we even have to write that?
Because that's telling you what you're doing. It's like writing a square root over a square. It's an operation. Okay, so then when I integrate it, well, you have x to the negative 3 plus 1 over negative 3 plus 1 plus c. That's the integration rule that we're using. So x to the negative 3 plus 1 is x to the what? X to the negative 2 over negative 2 plus c. So once I have a negative exponent, it needs to go where? Okay, so negative 1 over 2x squared plus c.
Why is it negative on top?
Because I don't like to put my negatives in the denominator. If you want to leave it in the denominator, that's perfectly fine. Now, I personally would not write this sideways like this chart. Okay? I would write it down. Each step of these would be a step down. But they have it, I just put them all on one slide. So I will show you my next ones. But when you have 9 through 14, they have a chart, guys. The chart, I don't care. These are the steps we did in every single one, yes? Those are the steps. Okay, so how can we write the integral of the square root of x dx?
X to the half.
X to the half dx. So this is my power rule that I'm using, right? Forgot my plus c. So x to the 1/2 plus 1 over 1/2 plus 1 plus c. So 1/2 plus 1 is what fraction?
3 halves.
So I have x to the 3/2 over 3/2 plus c, but I can't leave it like that. I have to multiply by the reciprocal. When I divide fractions, I multiply by the reciprocal. So that would be 2/3. That looked like a negative because it made a line. 2/3 x to the 3/2 plus c.
Hold on. So you took 3 over 2. So like, because you like had to multiply it? Because like,
I'm dividing by...
no, like, I know, like,
Oh.
you're dividing the fractions, but like, in order to divide fractions, you have to multiply by the reciprocal.
Mhm.
So you took 3 over 2 times 2 over 3? Or no?
No, because I have... It's like I have x to the 3/2 divided by 3 over 2. Yes? Which would be x to the 3/2 times 2 over 3, wouldn't it?
Yeah.
So that's why I have that.
Oh, okay.
Okay. So now we got to rewrite this. And you will have 2 with trig functions today. 2 is a constant, yes?
Mm-hmm.
So I can bring it out front. So I have 2, the integral of sine of x dx. Yes? So I'm going to have 2. Okay, and this is where you have to just know, what is sine the derivative of? Negative cosine. Because the derivative of cosine is negative sine, right? But we have a positive. So it would be negative cosine of x plus c. So that would be negative 2 cosine of x plus c. So the trig ones, you just have to know your trig rules. There's no addition, subtraction to that, because that wasn't one when we did the trig, right? You just had to know that the derivative of sine was cosine, derivative of cosine was negative sine. Okay. So the key thing to do today is make sure you rewrite it in something you can work with to use the power rule for integration. Okay. Now, you will have some where you have more than one term added or subtracted, and I think we have a couple different ones here. Okay, now these I'm going to work down like I would on a paper. I would never work across because it blends the steps together. So I have the integral of dx. What is in front of the dx that's not there?
1.
A 1. Okay, so if it's 1, anything to what power is 1? 0. So what we need, oops, jumped on me, sorry. So what I need to think in my head or write on my paper for today is 1 dx, correct? Wait, not 1, that's not what I said, anything to the, so I have x to the 0 dx, don't I? So then my power rule is x to the n plus 1 over n plus 1, correct?
I thought x to the first degree was always 1.
No, x to the 0 is always 1. X to the first degree would be whatever x is. So
That's 7.
x to the 0 is 1. Okay, so 0 plus 1 is what? 1. So I just get x plus c, correct? Now, this is one where there are 2 terms, correct? So we're going to rewrite it as the integral of x dx plus the integral of 2 dx. And we're going to work them as 2 different problems. Now this 2 could come out in front here, couldn't it?
Yeah.
If you wanted to, but it's just 2, x to the what? If it's just a 2, it's 2, x to the 0 power.
0.
So this is going to apply over here, isn't it? That we just got done doing. So on the first one I have 1, and 1 plus 1 is what? 2. So I have x squared over 2. 1 plus 1. Okay. Plus 2x plus what? C. And you'll probably want to write it as 1/2 y equals 1/2 x squared plus 2x plus c. Is that any different than what I just had? No, I just brought the 1 off so I didn't have to look at it together. So am I going to want to write this out every time as they get longer and longer and longer, like here? No. But am I going to take them individually? Yes. Okay, so we're going to go through this one again and break it up. This right here is a term, yes? What can I do with the 3? Bring it out in front. So I have 3, the integral of x to the 4th dx minus 5, the integral of x squared dx plus the integral of x dx. Before we go on, I want to make sure everybody understands what we just did. Where'd the 3 come from?
You took it up front.
It's the coefficient of x to the 4th, correct? Where'd the negative 5 come from?
Coefficient of
X squared.
Of x squared. And the last one, I didn't bring anything because the coefficient is 1. By doing that, it allows me to use the basic power rule without stretching my brain too far.
Why is there a dx there? I'm like,
Because you're taking this is one problem minus this problem plus
Oh.
this problem. There's a dx because that is the dx is the variable we are integrating. That's all it's telling me. You are finding the integral of x to the 4th with respect to x. You're finding the integral of x squared with respect to x. You're finding the integral of x with respect to x. Just like we did implicit, remember when we did implicit differentiation, we eventually will do implicit integration also. So that's why it's there. Okay, so 4 plus 1 is what? 5. So it's going to be x to the 5th over what? 5?
yeah.
Minus 5. What's 2 plus 1? 3. So x to the 3rd over 3. Plus, and there's a 1 here, right? What's 1 plus 1? 2. So x squared over 2 plus c. Shelby, you sleeping on me?
No, I'm not. I'm just dying.
So what we have is y equals 3/5 x to the 5th minus 5/3 x to the 3rd plus 1/2 x to the 2nd plus c. Now, we are going to have to plug things in here, and we got 3 fractions with uncommon denominators, yes?
Yes.
Yes? Okay, what is the number that 5, 3, and 2 all go into?
30.
30, right? Everyone following? So guess what I'm going to factor out? I'm going to factor out 1/30 x to the what?
30th.
Nope. I got 5, 3, and 2. X to the what? I got 5, 3, and 2. What do they all have in common?
2.
2. I have x squared in common, yes? Look, I got x to the 5th, x cubed, x squared, yes? Don't they all have 2 x's? Okay, so x squared. Remember, when I factor out 1/30, I'm really multiplying by 30, yes? So 5 goes into 30 how many times? 6 times 3 is 18. 18x to the what?
18x to 1.
I took out 2 from 5 is 3. Okay, 3 goes into 30 how many times? 10. 10 times negative 5 is negative 50. X to the first? Yes? 2 goes into 30 how many times? 15. 15 times 1 is 15. And we took the x already, yes? Plus c. Now, why did I put plus c outside of the brackets? Because did we take an x to the 2nd out of c? No. So if I had to plug an x in here, would it be much easier now without having to get common denominators with all of them?
Yeah.
Yes.
I'm really confused
But what?
about doing the whole 130 thing, because if you're multiplying all the fractions by 30, which is 30 over 1,
Right. So 5 goes into 36 times. So you have 6 times 3 is 18. So you have 30 times 3/5. Yes?
Yeah.
And 30 times
What's this?
5/3.
Yeah.
Got it now? Okay. And this is where we had, that's why I kept pushing you to practice doing that when we were doing that, when we had the quotient rule. Because we are going to solve this equation right here. We are going to figure out what C is. And it's going to be much easier to do with this version of the problem than with what we had here, isn't it? So when you stop simplifying is when it looks the easiest to plug things in. Okay, and we're going to continue working on that all the time. Okay, so we have to rewrite before we integrate. Well, I have not, on this list, there are other rules here, but I have not given you any of them, have I? No. So we need to rewrite this in a way we can use it. So this would be the integral of x to the 1/2 times x plus 1, wouldn't it?
Yeah.
Yeah? Oh, that'd be negative 1/2, wouldn't it? Sorry. Why is it negative?
You brought it up.
I brought it up. But I don't have anything for a product rule, do I? So guess what I need to do with this x to the negative 1/2? I need to distribute it. So I'm going to have the integral of x to the what? I have a 1 here, don't I? So 1 minus 1/2 is 1/2. And I'm going to spread it apart while I'm doing it. Plus, x to the negative 1/2 times 1 is what? So I have x to the negative 1/2. Now, do I have rules that I can deal with this?
Yeah.
Yes, I'm going to use my x to the n plus 1 over n plus 1. So I'm going to use again. Okay, so 1/2 plus 1 is what? 3 over 2. So I have x to the 3 over 2 over 3 over 2 plus negative 1/2 plus 1 is 1/2. So x to the 1/2 over 1/2 plus c. I always forget my y equals till the end. So now what do I need to do with both these fractions? Multiply by the reciprocal. So I'm going to have y equals 2/3 x to the 3/2 plus 2 x to the 1/2 plus c. Now when I think about plugging things in there, do you want to plug in a number, cube it, and then take the square root of it? I don't. Do you?
No.
No. So let's get rid of our fraction. Well, they both have a 2 in common, yes? And I don't want the 3, do I? No. So we are going to factor out 2/3. If they didn't have a 2 in common, I'd just take 1/3. Because the 2 is because they both have a 2. The 3 is because there's a 3rd in there, and I don't want it. Now I want to get, if I divide, I'm subtracting fractions, yes?
Yeah.
So what happens if I factor out an x to the 1/2? Would I get nicer numbers in there? Let's see. So what's the reciprocal? We're dividing by 2/3, so multiplying by what? 3/2. And I write it there just so I can see it. So 3/2 times 2/2 is 1, right? And 3/2 minus 1/2, because we're dividing fractions, gives you what? Did somebody say 1? Gives me 1, right?
Did you say 3 for the first one? Did you say 3
times 2/3. 3/2 times 2/3 would just give you 1, wouldn't it?
Yeah, I just got really confused because you wrote 2/3 x half on the bottom, so I didn't know. If you
Well, I'm factoring out 2/3, but I'm multiplying by the reciprocal. Okay? So then now I come to the next one. So 3/2 times 2. 2 and 2 reduce, yes?
3x.
And it's going to be plus 3. And I have 1/2 minus 1/2 is 0. So it's just 1. So I just have what? So would this be much easier to plug into? Yes. This one's kind of fun. Now this one, if you want to just watch me on this one. So this would be the integral of, well, can I write cosine in terms of sine? Cosine squared? Isn't sine squared plus cosine squared, what is that? Isn't it 1?
Yeah.
Yeah. And then I could subtract this over. So I could write it as sine over 1 minus sine squared. Yes? And then I could go on from there. Okay? So today, really work on those integration. There's not one quite like this there. And we'll go over those tomorrow and then solve for C.